The complexity of rocket science has worked itself into the common vernacular as the benchmark for describing a task too difficult for any one individual to accomplish. This is why it has attracted teams of students from across the country who know that by working together, they'll be up for the challenge.
Hello, does life exist on Mars? It's a simple answer when you look at pictures of the terrain, but how about underneath the surface? As the saying goes, don't judge life on Mars from the terrain. The only way to know for sure is to stick a rod in the ground, collect a sample, and analyze the chemical composition. The Soil Sample Collector, SSC for short, is a robust system that can collect up to 9 soil samples, store them in indexed bins, and stow away into a compact form factor to help with rover ground-level path traversal. The design is easy to service, utilizing 3D printed parts where feasible. It is modular and offers scalability by allowing adjustments to the number of bins without affecting the collection or stowage systems. It is also energy efficient, making it a prime candidate for replacing gas-guzzling sampling machines currently used in the agriculture industry. The future is green, or rather, red.
Hello, we are Team E, the Robotic Gripper team. We had to create an end effector, which is a robotic hand that allows a robot to pick up, manipulate, and interact with the world around it. The York University Robotics Society required such an end effector that would interface with our existing robotic arm and wrist. The end product requirements that we had to meet were size, mass, power consumption, and performance requirements. With that in mind, our mechanical team started looking into types of grippers and jaw configurations that would meet these requirements. We came up with this design in the end. We then printed it and tested the design thoroughly and made adjustments based on the results. We needed an electrical system that could interface over a CAN bus network and control all the aspects of the rover. We started on a breadboard and moved to a perf board for a finalized soldered design. Our testing approach included us testing the electrical and mechanical systems separately due to COVID and implying that both together will work in the end. Our results after our testing is we have 2 separate subsystems that are ready for integration by the Robotics Society.
Hello everyone, we are Team F and our project is to develop a web GUI for the York University Robotics Society rover. The rover team at York currently uses CLI, which is a command line interface to control the rover. This means they need multiple terminal windows open and it makes it inefficient and cumbersome, as seen in the example here. Controlling the rover also needs an installation of a bunch of software, including the robotics operating system, which only runs on Ubuntu. With the GUI we're developing, it'll be much easier to use as you'll be able to click buttons instead of typing to the command line. You'll also be able to control the rover using any device. That includes tablets and mobile phones. Now let's take a quick look at our final product.
Hi everyone, we are Team U, and our project was to perform verification testing on the current SS3U CubeSat design to ensure it's able to survive its mission duration. Over its lifetime, a spacecraft can experience different environmental stressors, which can cause damage to its structure and components.
This includes vibrational loading during the launch phase, as well as thermal loading due to the temperature distribution the CubeSat will experience while in the orbit.
To determine the satellite's response to these environments, we develop a finite element model for each of the major spacecraft environments and perform a finite element analysis. This is the process of breaking down the object into smaller components and outputting their reaction to external forces like radiation. The thermal and structural FEMs have different mesh settings depending on their geometry and material.
Output from this analysis include displacement and stress values at specific points in the model and can indicate if the part can withstand the load. These verification analyses are critical in design phase and will support mission's success.
We are Syed, Abel, Gabriel, and Tej, making up Team V, the electrical design team for a 3U CubeSat. Our project is funded by the Canadian Space Agency under the Canadian CubeSat project, and we are working as part of the electrical team for York University's Essence satellite. Our goal was to design and prototype 4 custom PCBs for the CubeSat. These boards held mission-critical components, such as the optical camera and proton detector payloads, and the attitude control system. One major component involved initializing a 30-minute startup timer, required once released from the International Space Station. Our work involved electrical schematic and PCB layout design, prototype testing, and procurement of the final product currently underway. Any questions?